Hello again, everyone. I'm Joe Pryweller, Director of Conference and Event Content for Plastics News. I want to welcome you to this webinar on demolding temperatures, presented by AMCO Polymers and organized by Plastics News. In this webinar, AMCO Polymers will help you understand demolding temperatures and how a DMA curve combined with an IR camera can optimize your cooling time. Let me introduce today's presenter. Sean Mertes is Principal Application Development Engineer at AMCO Polymers. Sean is a 31-year plastics veteran. He specializes in part design, mold design, material selection, and troubleshooting. During the course of the webinar, you can ask questions by opening the Q&A icon located at the top or bottom of your computer screen and then typing in your question. Your question will be answered in the order that it is received after the presentation portion of the webinar is completed. With that, let me turn the presentation over to Sean Mertes of AMCO Polymers. Sean, the floor is yours.
Awesome. Welcome, everybody. Thanks for attending. I really appreciate it. Let's get started. Okay. So, as Joe stated, I am Sean Mertes with AMCO Polymers. I'm the Senior Principal Application Development Engineer. Thanks for attending this demolding seminar. I'd like to give special thanks to Priscilla and Plastics News for setting this presentation up. Today, we're covering a topic that is near and dear to my heart and I've been working on for a few years now. Make sure to keep an open mind and ask questions to be discussed at the end of the presentation. Today, we'll be discussing how I think the cooling time should be controlled and understood by using DMA curves, how Moldflow actually determines cooling time, how dimensions are affected, and future plans and studies. In the end, I hope to show you a better way to optimize your cycle time and save lots of money. So before we get into the seminar, I need to show this legal disclaimer. Everything in this seminar is accumulation of findings through the years. Individual results may vary for your resin and molds. Is my screen advancing?
It sure is, Sean.
Perfect. All right. So the agenda, today we're going to discuss different ways to calculate cooling time. How do you do it? A lot of places just say, okay, I can estimate my fill time, my cool time, and just some people use a rule of thumb to say every wall thickness you need X amount of seconds, take it times 1.5 times the wall. Or we have something similar, it runs about this cycle time, or I think I can get it done in about 35 seconds or 40 seconds. We're gonna discuss DMA curves and how I think they can really assist in understanding demolding temperature, or basically the temperature of the part coming out of the tool. We're gonna discuss DSC techniques, filled versus unfilled resin, Autodesk or Moldflow technique, how they do it, what effects it has on dimensions, and then the thermal imaging camera. So this saying is one that I really like. It's basically to keep an open mind. The greatest enemy of knowledge is not ignorance. It's the illusion of knowledge. So many people have been doing things for years and years and years, and they just do it because that's the way they think it needs to be done. Hopefully we're going to kind of talk about some things that open your mind and allow some change. So what about cooling time? Cooling time of your cycle time, and basically that's how you make money as a molder, is you do not sell plastic parts, you sell machine time or conversion time. So the faster you can run your parts, the more money you can make. So basically you fill it, you pack it, you hold it. Everybody does scientific molding, systematic molding, decouple molding. Everybody knows and understands, you know, your viscosity curves, gate freeze, so on and so forth. But one thing that's really not discussed or covered is part cooling and plastification. So as you can see, cooling and plastification is probably 80+% of the cycle time, and yet it's typically ignored. And there's really not a seminar or class that you can kind of go to on this. So I kind of dug into it and said, okay, what can we do? Years ago, I was given an infrared camera and I went to one of my customers to mold these nylon fittings. These aren't actually the nylon fittings, but it's something similar to this, where they have different sizes. They have 1/2 inch and 3/8 and quarter and female and male and different interactions. And I said, okay, what kind of cycle time can we run? I said, well, it depends on which combination of tool we have, how many inserts we have, and the wall thickness. So I said, all right, I'm gonna use my infrared camera and I'm gonna find the hottest parts. and we're going to link my cycle time to the hottest part of my thickest section. So I started doing it, and I noticed right around 210 degrees, 200, 210 degrees, my parts are coming out and they're just kind of distorting by the weight, or you can push on them and they become oval very, very quickly. So anything under about 200 degrees, they're pretty much set up and pretty rigid and they kind of hold their shape. So I said, okay, we're going to run my cycle or my cooling, and I'm going to keep decreasing my cooling time until my hottest part comes out about 200 degrees, and knowing and understanding that my mold's going to heat up and over time things are going to change a little bit, but I want to be around that 200, 210 degrees. So I went through and I said, okay, from Advanced Polymer Engineering, there was this software that I used, and I put in as a nylon 6, mold temperature of 100 degrees, melt temp 475, and the wall stock of this one was about 0.125. So I put this in and it said the calculated cycle time was 25.3 seconds. But my favorite part is I like this T sub X right here. So it's from a lookup table. And basically what it does, it says your T sub X, your demolding temperature, is heat distortion at 66 minus 30 degrees, HDT minus 30 degrees. So it says, okay, if my heat deflection temperature is 356, subtract 30 degrees from there, it should eject at 326 degrees. So 326 is here, and I could put an override in there if I wanted to, but this is just normally what comes up. And I started thinking, I'm like, wait a minute, it says I should eject my part at 326. And if I get over 210, 220, my part comes out too soft. I'm like, there's no way I could eject this part, an unfilled nylon 6 at 326. So I started thinking, I'm like, well, maybe my HDT is wrong. So there's an app that I have on my phone. It's an iMolder app. It's a free app. And I looked at the HDT. This HDT here is 365 to 375 degrees. And I'm thinking, well, wait a minute, that HDT is actually higher than my 356. So even if I subtract 30 degrees from here, I'm still 335. Well, what's going on? So my observations were, when I get to approximately 200 degrees, when I get above 200 degrees, the parts come off soft and flexible. They deform, they're too hot. HDT says this, 326 degrees, it's not working, why not? So I said, all right, what else is out there? There's a gentleman by the name of Bill Tobin who gave me this chart. And I'm like, oh, this is kind of cool. It actually says what my material is. So I went to PA6, close tolerance, commercial tolerance, commodity tolerance. I'm like, oh, that's kind of right where I am, 194 to 230. The longer I hold it in my tool, the tighter the tolerance. And if I really want a close tolerance, I hold in the tool for a lot longer and use the mold as a fixture. I'm like, oh, that's pretty good. But I want to know, what's close commercial commodity tolerance. So I went to SPE, and basically they just says commercial tolerance is just, fit, form, function. And if you need to hold a tighter tolerance, you have a plus or minus 1, and this could be plus or minus 3 or 4. So find commercial or looser tolerance. I started doing this, and then I started seeing different ways of doing things until I was introduced to what's called a DMA curve. This is a dynamic mechanical analysis curve, and it's one of my favorite curves. I love looking at this curve. There's so much to gain from it. So basically, let me explain it here. I have my elastic modulus, which is basically my flex modulus, and it's measured in megapascals on this one. And I have my temperature. So I have my temperature measured in degrees C, and my modulus in megapascals. So room temperature is about 23 degrees C, 73 degrees Fahrenheit. I happen to know that a million modulus is right around 7,000 megapascals. So all these start at room temperature, right around a million or above a million. So these are all 30% glass filled PBT, PET, nylon 6,6, and syntactic polystyrene or Xerac. So these all have modulus. So if you look at a data sheet, they say, all right, they're a million modulus and high HDTs. I'm like, okay, these are pretty cool. The thing I like about these is this modulus up here at the very, very top until it starts moving down. Where it starts transforming here is my glass transition temperature, my TG. So right here starts coming down, here again starts coming down. So everything up here is I have amorphous and crystalline zones. Glass transition temperature is the temperature where my amorphous zones begin to move freely. So here I have amorphous and crystalline zones up here at the top. As my amorphous zones begin to loosen up and move freely, my modulus starts to drop. So everything down here, when I get past my TG, this is 100% crystalline. My amorphous zones are soft and flexible. They're really not holding much modulus. So down here, I'm crystalline only. Up here, I'm amorphous and crystalline. So if you look at the difference between up here and down here and subtract the difference, that tells you how crystalline a polymer is. In this case, I lose the most modulus between crystalline amorphous and strictly crystalline. So SPS is not as crystalline as my nylon 6.6. I did not lose as much from up here to this transition here. My nylon 6.6 is more crystalline. If this were to stay across and dip a little bit, I'd have higher crystallinity, so on and so forth. But these curves are amazing. I love looking at these curves. So we have amorphous resin. My amorphous resin does not have any crystalline zones. So once my amorphous, being 100% amorphous, as soon as I hit my TG, my amorphous zone starts to soften and loosen, and I lose all my modulus. Here's my semi-crystalline. Everything's considered semi-crystalline because there's amorphous zones, crystalline zones. So I go through my TG, my glass transition temperature. Here I'm amorphous and crystalline. I go through my TG. Here's my crystalline only. I was actually sitting in a seminar, and I remember the day, it was probably 10 years ago, and I looked at this and I had an aha moment. I just remembered back. I'm like 200 degrees, my part's coming out, and it hit me. I'm like, wait a minute. What I'm looking at here is this is where my TG starts building modulus. So as a processor, as a designer, you read this left to right. Here's room temperature. What happens as they get hotter? As a processor, we need to read it right to left. So we're out here processing way out here on the right side. At what temperature can I eject? And I started noticing at, 212 degrees is 100 degrees C. It's right here at about 200 degrees, 93 degrees C. I start building modulus, which is exactly what I noticed during my processing days. And I'm thinking to myself, this curve right here tells me everything I need to know about when I can eject, because it tells me when I'm starting to build my modulus. So I started doing some investigation and started thinking about these DMA curves and what they mean to me. So I started thinking, all right, are these all wrong? What does HDT represent? Bill Tobin here, he had, he was close, but where do these numbers come from? This one is HDT minus 30 method. Are they getting it from HDT or what? And I did some more research and I found out that heat deflection temperature, there's a gentleman by the name of Michael Takamori from GE Plastics. He calculated the modulus associated with 66 PSI is 29,000. So if you think about a very, very soft, elastic, Sanaprene type or GLS or some very, very flexible, low modulus, 29,000 PSI is very low modulus. 264 is about 116. So this is the modulus of a very soft copolymer polypropylene. So basically you could take something that has a modulus of 1,000,000 and at 264, it says something that's 1,000,000 PSI, heat it up until it feels like a very soft propylene. Well, that doesn't give me very much rigidity, doesn't give me very much stiffness. So my HDTs, I'm like, well, I'm not necessarily sure that they're realistic because sometimes I want to maintain rigidity. So I started looking at these. And if we go back to IDS Prospector or UL Prospector now, and I will look on a data sheet and I say, okay, I want to have a modulus of 1,000,000 PSI, which I said about 7,000 megapascals at room temperature. So these are both above 1,000,000. And I want HDT or DTUL, deflection temperature under load, above 200 degrees C or 400 degrees Fahrenheit. I would look on a Prospector data sheet and these would be two that would come up. They look very, very similar. I'm like, oh, they're really, really good. They both have high HDTs. They both have high modulus on a data sheet. They look phenomenal. However, in realistic, when I really get out to my 200 degrees C, my modulus here is below 2,000 megapascals for this PBT because it's crystalline. I lost, it went through my TG. Here's my crystalline only. My PEI or my ULTEM is amorphous only. So right here, I'm all the way out here. I still have high modulus. I'm still above 1,000,000 modulus at 200 degrees. So if I need something at 200 degrees under the hood of a car or something that's going to be for a firefighter, a life-saving event, I don't want something that's very, very soft and flexible and can collapse on me. I want something that's very, very rigid. So we need to know and understand that data sheets are single point data. I don't necessarily like HDT. I like looking at the DMA curves and actually seeing multi-point data. So I started asking, I'm like, okay, this is great information. How does Moldflow do it? So I went to Moldflow and I asked them through AIM Beaumont and said, can you show me how they get an amorphous, what they do? So they said, all right, we use a DSC and the intersection, the extrapolated baseline, so on and so forth. I don't want to go through this and kind of bore you, but they said this peak here, the transition temperature halfway point, is where we get it. So I went to Madison Group and said, hey, do you have a polycarbonate? They actually have a polycarbonate PET compounds like a xenoi or a macro blend. So here is my DMA and here's my DSC. And I did my cross reference of this peak here, the intersection where it is, and it comes down here. I'm like, okay, that kind of makes sense. Here's my glass transition of the PET portion. But I have a lot of modulus, and notice the slope of this curve here. When I start getting from room temperature right here, the slope comes down and I'm losing heat. My amorphous zones are starting to soften, but I stay pretty solid. And then right here is where my polycarbonate, right around 300 degrees Fahrenheit, my polycarbonate loses its modulus and falls off. So it's, yeah, the amorphous and Moldflow, that's very accurate. How about crystalline resonance? So crystalline, I have a peak, and this peak here tells you how crystalline you are, the height of the peak, the depth of the peak, so on and so forth. The intersection, extrapolated lines, the ejection temperature. Here's the transition temperature, so on and so forth. So once again, I went to Madison Group. They ran a DMA, which is my brown or red curve here. My DSC is here. This is a PBT PET compound. And here's my curve right here. I did my intersection. I'm like, wait a minute. Here's where I lost a lot of my TG. Here I'm crystalline only. So right here is basically where my T sub M, my melting point. So basically, according to Moldflow, from what they were doing a few years back, they're saying as soon as it's molten, kick the part out. And we know, because the nylon that I ran, that's not true. So I went back in and said, okay, show me your crystalline ejection temperatures for Moldflow. So DuPont, Zytel 101, here's BASF, Lanxess, Duraton, and they're saying my ejection temperatures 374, 338, way, way, way higher than realistic polymers can do in the unfilled states. Once again, I noticed that right around, for a nylon 6, right around 200, 210 degrees, and that's where my TG is. So we need to understand better about what my glass transition temperature is. Glass transition temperature for my amorphous resins, this is the guideline of where we should hopefully be able to eject, or maybe even slightly hotter. So we did a real world test. I was working with an OEM that wanted to save money on a cycle time. They were running a FR PC ABS, and we sent in an FR PC to compete against it. I was not able to attend the sample, but I did call the sample tech, and they said, oh, it was great. It was a drop-in resin, ran the same cycle. I said, did you run, a cycle time faster or cooling or anything? And he goes, nope, I just dropped it in. It worked great. I said, well, they did not necessarily understand demolding temperatures, because in FRPC ABS, because the ABS component, I have lower heat. So according to Moldflow, I can eject FRPC ABS at 188.6. I can eject FRPC according to Moldflow at 257 degrees. So if I'm running this and I'm ejecting at 188, and I know that my ejection right here, whatever I can eject, my modulus is, say, slightly above 250,000 modulus, I can be way out here, well above 300 and some degrees, or close to 300 degrees, and have that exact same modulus. So these both have different thermodiffusivities, but we need to know and understand that my ejection temperature for different resins are different. So once again, many variables affect your demolding temperature. Your demolding temperature is based on thermodiffusivity of the resin. ABS has a different thermodiffusivity than PC, which is different than polyvinyl chloride, PVC, polycarbonate, ABS. Mold steel, thermoconductivity of steel. Am I running P20, H17, stainless steel? How effective are my water lines? What's my pitch? What's my depth? Do I not have hot spots? And make sure that I have turbulent flow. My portion that I'm talking about today is cooling time. I'm not really talking about my different changing resins. I'm not talking about my steel. This is, what we have. All I'm doing is I'm saying, what cooling time can I adjust in order to get my part out so it comes out without warping or pin push or having issues. And the last one, but not least, is packing pressure. Plastic needs to remain contact with the steel and the core. So higher my packing pressure, typically I keep better contact with the steel, which allows me better thermal transfer between the plastic and the steel. So I went to PC and I started doing some testing. I went to PC, went back to Tobin's thing. He says here 140 to 185 for close, 185 to 230 for commercial, and 230 to 266 for commodity. I'm like, oh, okay, that's pretty good. So I pulled up a DMA. This DMA is actually for a Macrolon 2407, I believe. And it says, okay, close tolerance is 140 to 185, which is way back here, close. My modulus is 288, 625. Commercial, my modulus is just slightly higher by, 1000 PSI. And here's my modulus is slightly higher again. So they're saying, wait a minute, as I get out here, you're saying you get a tighter tolerance out here? And that kind of confused me because I'm like, wait a minute, my modulus doesn't say change. Warp, pin push, all has to do with the modulus of the steel. Obviously, your draft that you have and ejector pin size make a difference, but does 1000 PSI really make a difference? So here I wanted to find out percent difference. So I went all the way out here at 288, 625, which is back here at 176, all the way out to 265. I went out to 291 degrees. So 291 degrees all the way back to here is an 8% difference. So my question is does 8% difference in modulus make a difference in dimensions, warpage, so on and so forth? Warpage basically to me is defined as my internal stress of the plastic is stronger than my modulus and it causes it to tend to warp. If I have my modulus and it's set up strong enough and I can withstand that internal stresses, I should not have much warpage. So I went to the press. Actually, I was working with a good friend of mine, Chad Johnson at Phillips Metasize Molex. We're working on a job here and it has a 7-second cooling time. You'll notice that my part come out at 296 degrees. And then I went all the way and I added 3 seconds, 7, 9, 11, 13, 15, 17, 19, 21. And obviously the longer I keep it in the tool, my part comes out cooler. So then I went back again. I said, okay, start here. Here was 1017, I went to 1020, ran the same thing backwards from 21 all the way back to 7, and I put it into a graph. And you'll notice that these are very, very close, 296.6 to 300, 282 to 290. This is a little bit of a gap, I'm not sure there. 278, 278, 269, 263, 258. Really good, close communications, knowing that I started here, went down, and then went back down here and all the way back up again. I took an average of these and I subtracted. So I wanted to find out how much am I losing per second? So if I know here 298 at 7 seconds and I went down to 286, I lost 12 degrees in 2 seconds. So approximately 6 degrees a second. Between here and here, I lost 8 degrees. So 4 degrees a second here to here. I took an average about 7.8 per 2 seconds for approximately 4 degrees a second removal. So I said, okay, if I know that my curve can be out here, where can I eject? I know that I can be out here. So we picked out here beyond the point, 289 degrees. This right here says 286 is my average, but my actual is actually 289. And I went here, we actually ran it and we held tolerance. We had no issues or problems with holding tolerance, even though I'm down here starting to fall off, but my modulus is still high enough to hold my dimensions. Now remember, you must include this sprue and runner as well. If you have a thick sprue and runner, I was working with a customer and I was explaining this concept to them for polycarbonate. They said, there's no way, Sean, I can run that fast. We actually took a thermal camera. The parts are coming out at say 170, 180 degrees. And obviously we looked at the hot sprue here. My sprue here is 312 degrees. So this hot spot right here, 312 degrees, I'm way out here. If you took this, it was very bendable, so on and so forth. So this case, my sprue and runner was my limiting factor. So I would say if you want to run a faster cycle time, I need to downsize my sprue and runners, put extra cooling in there, maybe recut channels. But in this case, my sprue and runner was my limiting factor, and we need to discuss that. So we did another real life scenario. This one is really interesting to me. It's an ABS. Here's a little part, and we wanted to measure the gap between here. So basically what we did is we started running as fast as we could, and we said, okay, how hot? 260 degrees, 230, 215, all the way colder. And I noticed at 190 degrees, my dimensions started slipping. And I talked to a lot of people and they tell me this. They said, well, what we do is we start running, decreasing my cooling time, increasing my demolding temperature until all of a sudden my dimensions start slipping. Once my dimensions start slipping, I know that that's as hot as I can run and I need to be back here. So according to this scenario, I would say I can't run at 190. I need to be at least 180. Okay, well, that makes sense because that, maybe even 170. I don't know what 180 is. But I looked at my curve here and I'm like, wait a minute, 170, 180, I would think I should be out at 210, 211. Why am I moving too much? So I looked at this again, same 100 degrees. So I said, let's run a hotter mold temperature. So I actually ran a hotter mold temperature. I went from 100 degrees Fahrenheit to 150 degrees Fahrenheit. And notice I got all the way out here to 235 degrees. And my dimensions, my max to min, they don't really change that much. So my question is why would running a hotter mold temp provide us with better dimensions? Once again, we kind of discussed this. To me, you have molded in stress. This molded in stress wants it to bend and curve and do different things. And if my modulus is strong enough to withstand that internal stress, it's not going to move. It's still going to have that internal stress in there, but it's not actually going to move and deflect and make changes. I like thinking about it when I give my seminars as a false ceiling. If I jump up and I hang on the false ceiling, I'm going to deflect that false ceiling inward, like sink. If that false ceiling is connected to a 2x10 or a 2x12, and I hang on that same metal bracket that's connected to a 2x12, my weight isn't going to deflect that ceiling because that 2x12 is strong enough to withstand that internal pressure. So I like using his DMA curves and saying, okay, where do I think I need to be? I think I should be around 210, 211. And you need to have these curves because otherwise I would have been back here at 175 and been losing 4 degrees a second, and I could take out another 20 degrees, 5 seconds of cycle time. So molded in stress causes warpage. We run a hotter mold. We eject at hotter temperatures. We get a less stressed part. We run faster cycle. It's opposite of what I would have thought. We always thought cold tools run faster cycles. And in this case, I ran a hotter tool. I was working with Mr. Seppi, and he told me one of the things with annealing parts to relieve stress is people cool the plastic too quickly after they anneal. He said, you want a nice slow heating. So another advantage of this demolding temperature is kicking my part out. I pull out, let's say maybe a degree a second, and that's probably pushing it a little bit. Inside my tool, my polycarbonate, I pulled out about 4 degrees a second. Here's an ABS. I pulled out about 3.3 degrees a second. Notice that at 20-second cooling time, I was about a little over 200 degrees Fahrenheit. And then right here, I'm about 190. So the difference between here is 10 degrees, 20 to 23 seconds. That's 3 seconds. So about 3.3 degrees per second. Is this optimum? This is just one tool. I need to verify. And I want to check polycarbonate versus ABS versus ASA versus PVC versus blends and PC ABS. So I want to find out what my optimum is. But the important point of this one is my dimensions. My dimensions never changed. We had an ovality, my roundness stayed the same, everything stayed very, very similar because my modulus was strong enough to overcome everything. So my dimensions do not change. So we need to better understand TG, glass transition temperature. And once again, glass transition temperature is the temperature where the amorphous zones begin to move freely. This is really the key for my nylon 6 and 6.6. Don't think of glass transition as glass reinforced. Glass transition and glass fiber are totally different, but we're going to talk about glass reinforced. So here we have glass reinforced. So as I add my filler, I have an unfilled. This is for nylon 6. Notice that my glass transition temperature is right there, same glass transition temperature. As I go up and add fillers, my glass transition temperature stays the same. My dimensions over here stay the same. This curve looks almost identical. So my TG stays the same. My T sub M, my melting point, stays the same. But everything just starts increasing here. So imagine that if I need an ejection of A, how much ejection pressure it takes to eject my part. Here's my, right there at that 200 degrees Fahrenheit or 100 degrees Celsius. All right, that's kind of where I found my nylon. But now if I'm running out here with a glass filled, 33% glass filled, I could probably get way out here a lot closer to my T sub M, and I can eject way out here. So looking at these DMA curves and knowing and understanding how much ejection force I may possibly need, I can find out what this is. I also want to learn the slope of these curves, the slope of my nylon right here, post TG to TM, the slope of this line. I want to know what this is for nylon 666, PET, PBT, all my different types of resins. But imagine that I add C. This is an ejection force C. For some reason, I have small pins, big draft. I couldn't even run an unfilled nylon. At 14% glass, I bring this over, it intersects here. I would say I'd be able to eject this at about 70 degrees Celsius. As I start getting over here to my 33% glass, I can eject at about 175 degrees Celsius. So these curves tell me everything I need to know for ejection. Crystalline resins are more difficult, but amorphous resins, much easier. So here's all my crystalline resins. My polyethylene, glass transition temperature, minus 200 to minus 184, polypropylene. And here I have my melting point. Here's where they actually melt. Here's my glass transition. Once again, semi-crystalline means I have amorphous and crystalline. You have a glass transition and a melting point. For amorphous, I only have glass transition. But what if the glass transition temperature is below room temperature? So I'm never really going to get to room temperature to my glass transition for polypropylene, polyethylene, and acetal. They have glass transition temperatures below room temperature. So these are ones that we need to discuss more, and future things I want to talk about polyethylene, polypropylene, TPO, acetal, but I want to determine the slope of these curves and know exactly what it is. I do know from Moldflow when we've doing different things that polypropylene ejects at approximately 230 degrees Fahrenheit. We may be a little hotter, maybe a little colder, but right around 230, 240 degrees Fahrenheit, polypropylene can eject, starts getting soft, and you start getting hotter than that. So I showed this to one of my good customers. Mike Birrell actually went to AIM class, and he provided this little statement here. Plastec has seen significant reduction in cycle times when monitoring demolding temperatures in relation to glass transition temperature. This has been equally beneficial to our company and customers in cost-saving initiatives. In a time of period of 5 months since implementation, we've seen cost reduction of over $100,000. Resources to use this are less than 8 man-hours a week. Mike Birrell. Here they did, this was back in 2019. I just haven't asked them to update this because this is just great information. But the original cycle time was 93 seconds. The new cycle time was 79 seconds. They saved 15% cycle time. Here on this one, 55 seconds to 26 seconds. Now, all these actually went through quality. They tested them. They verified that the dimensions never changed. And all the cycle time savings were theirs to keep or to share with the customer. So these are all things that just low-hanging fruit. It's things that you can do that's quick, it's easy. I may come in and actually test your demolding temperature and say, you know what? You're running it exactly where you need to be. That customer I told you with that sprue, that thicker sprue, we couldn't necessarily run that any faster. I can give you a pat on the back and saying, you're doing the best. How many times has an OEM or someone come to you and say, well, the customer down the street says they can run a faster cycle? Well, guess what? If you're doing scientific demolding or scientific decouple molding, systematic molding, you're filling as fast as possible, gate freeze, I've optimized my cooling time, plastification time. There's really nothing you can do to be any faster. So in summary, we've discussed the 4 methods for calculating demolding temperature, HDT minus 30, which is the calculation. Bill Tobin had his little spreadsheet, which got me started the right direction, but he says that the longer you hold it in the press, the better, tighter tolerance you have. And I'm not sure I agree with that. Moldflow uses the DSC, which is good for amorphous. I did talk to him a little bit more, and they said that they use that calculation, but they also have a correlation factor that they put in so that they know that they can eject nylon at 300 some degrees. They know it's right around 210 degrees. So they put a correlation factor in there. And I think they are starting to use DMAs to understand it, but these DMAs are significantly a glimpse to the answer. But now what we need to do is we need to make sure that we use thermal cameras with max temperature. I have a lot of my customers that have thermal cameras, and you have to move that little dot around and then find out where my maximum temperature is. Make sure that you have a good thermal camera that records max temperature, and it works really good. So what's next? I've been working on this for a while, and I have a few things next here. So These are things that we're looking to partner with people. We want to quantify the slope of the curve, T sub M to T sub G. So we talked about that. The slope of my SPS right here, the slope of my PBT, the slope of this PET, nylon. This slope tells me where I can eject and if I need to be here, if it's filled or unfilled. That makes a lot of sense. I also want to know when I'm processing out here, way to the right, much hotter than my T sub M. So what is the slope of this curve for what I can come out? Like I said, nylon, we found out, or for polycarbonate, I found out it's about 4 degrees a second, ABS about 3.3 degrees a second. But what is it out here for my processing temperature till I get to my T sub M? Does that match that same slope that I have here? How about for amorphous? Quantify the slope of my amorphous. So here is a steady decrease in modulus as my temperature is increased till I get out here. Here's my loss modulus, here's my tan delta, so much more on these DMA curves that I love to see. But here my loss modulus is the highest, where they say my T sub M or my T sub G is. That's where I can process. But the slope of this helps me determine how much heat can come out, this slope, and thermodiffusivity. So I want to quantify PC versus ABS versus PC ABS versus HIPS, many more. We've seen polycarbonate approximately 3.9 degrees I've shown you, and ABS was 3.3. I'm not sure if that's optimum. I may be able to run an aluminum tool and get out 3, 4, 5 degrees a second. But plastic only gives up heat as quickly as it wants to give up heat. So I can't take heat away faster than the thermodiffusivity will give it up. So my goal is, I would like to know approximately exactly what I can do and say the best I can do for polycarbonate, and I'm making up this number, say 4 degrees. I can walk up to your press and polycarbonate and say, add 2 seconds to my cooling time. 2 seconds should add 8 degrees to my ejection temperature. So it should come out 8 degrees colder. And if it comes out 8 degrees colder, I can patch on the back, say, you have efficient cooling. If you add 2 seconds, and I should be able to pull out 4 degrees a second, and you add 2 seconds, and a part only comes out 4 degrees colder, well, guess what? You probably may not have turbulent flow. There may be someone else that's doing conformal cooling or something different and has better efficient cooling than you do. But at least you know this now. So we need to understand the slope from processing temperature to my T sub M or my T sub G. As I'm processing out here, what's the slope, or how much degrees a second can I pull up from where my processing melt temperature is, say 425 degrees, until I get to my 300 degrees or 280 degrees for ABS. I need to know is the same slope for crystalline versus amorphous. I need to understand if we can change the slope. So this slope that we're talking about is this slope right here. I want to know this slope of this curve. How many degrees am I pulling out per second? This slope of this curve is what I would consider to be the thermodiffusivity of the resin. Can I change this slope? Because if I'm more steep and I can pull more heat out quicker, that's going to give me faster cycle times. So what can I do? What about an endothermic foaming agent? How much does that necessarily change? What about different fillers? Does glass fiber, does hemp, does mineral, calcium carbonate, talc, do they change, pull heat out differently? What effect does a nucleating agent have on a slope? Nucleating agents allow me to build crystals quicker at higher temperatures. So I should be able to eject my part out a little hotter. So then the next question is, does 10-degree mold temperature or 10-degree melt temperature make a larger difference in demolding temperature? So if I add 10 degrees to my mold, does my demolding temperature come out 10 degrees hotter? Or does it only come out 5 degrees hotter, maybe 7 degrees hotter? Which has the bigger effect, 10-degree mold or 10-degree melt? We do know that hotter molds provide less molded in stress, but what happens to my melt temperature? So these are all things that are future tasks that I want to do. It all just takes time, money, having a press that can do it, and infrared camera, and then document and understand. So I want to thank you for this. In conclusion, wrap up what we're covered today. I want to give a shout out to a few special people who helped me tremendously. Priscilla and Mervick from AMCO marketing team, Plastics News team, AIM American Injection Molding, John Beaumont and his BTI team, Mike Sepe, John Bazzelli, Adam Kranschuster from UW Stout, few working friends such as Thomas Schoen at Aeroplax, Chad Johnson at Molex, and especially Ross Jackson, David Lynn Smith from AMCO. If you found this seminar useful, we're looking for companies to partner with on the next step of the process. You can reach out to me or the AMCO tech team if you'd like to receive more information or work one-on-one with our engineering team. If you'd like a copy of this presentation, please reach out to our tech team. Here's the AMCO tech email and phone number. We are now open to questions.
Thanks, Sean. Great presentation. I appreciate you walking through us all the steps that you went through to get the point you did, and it sounds like there's still some work to be done too at the same time. So that's terrific. As Sean said, they're ready to take questions. To ask a question, you can go on to the Q&A icon at the top or bottom of your computer screen and type in your question, and your question will be answered in the order that they are received. Sean, I want to start with one question that came in. This is from a customer who's shown this to somebody a few months ago, and when this was tried, recover time controlled my demolding temperature, and I was not able to get to the desired demolding temperature I wanted. What should I do?
You know, that is one of the disadvantages that I've seen where can somebody run faster? Like I said, if you optimize everything and everything is based on data and say, I can kick out at 310 degrees, but because the wall is so thin, by the time I plasticate, it all has to do with your shot size. So I have had a couple of customers that they put it into a larger barrel because they have a small shot, small diameter. I need a long stroke or a long length, and then I need a plastic it and need to rip back to get back, and they may not be able to get back in time. So the two things that I've seen or heard people do is they put it into a larger shot size. So therefore the larger diameter, I need less stroke. So I don't have as many rotations to get back. Even though a larger press may cost you more money, but if I can save 5, 6, 7, 10 seconds of cycle time, if I go from a 300 ton to a 500 ton, it may be worthwhile in the long run, or just maybe a larger shot size. We like small shot sizes for consistency, for intensification ratio, but in the case of demolding, we want to get back as fast as possible. The second thing that I had a couple of customers, what they do is they put a nozzle shutoff on so that as they're plasticating or recovering, they can actually have the mold open and they can be opening the mold during plastification. So that's one that's really unique, and I really like that application.
Excellent. Well, a few other questions have come in here. How do I use a DMA curve to pick the demolding temperature? Is it just past the bend to the hotter side?
That's a good question. So as we talked about on your DMA curves, for the amorphous, typically, yeah, once you start getting out towards the bottom end and you can start seeing as you're coming down, it all has to do with the initial modulus you're starting with. Let's say that you're starting with an Ultem, which has a higher modulus than an ABS. It's going to be able to fall down that curve a little bit more than say an ABS or something that doesn't have quite the modulus. So I like going out to where it starts falling down and maybe, you know, just a small distance, you know, pick halfway down the bottom to the start of where it starts to fall. You know, I would like to optimally be somewhere in the middle, but I'd say probably middle or up is where it is. For my crystalline, if it's unfilled, you need to know what the TG is. So like for my nylons, polyesters, where that TG is, like I said, for my nylon 6, my glass transition temperature is right around that, you know, 200 degrees Fahrenheit. So I need to be to the left of that. If it's glass filled, I can be out a lot further. So a lot of it depends on what it is. If my TG is below room temperature, my propylenes, ethylenes, TPOs, acetals, we're never going to get to my TG. So a lot of it just has to do with the slope of that curve and where I have a high enough modulus based on draft, ejector pin size.
Good. Another question concerning materials. How do you do this for polypropylene or TPO materials? The person says here, I believe that drop-off is basically non-existent until very low temperatures are reached.
Polypropylene, polyethylene, and TPO are probably a little bit more of the unique, more difficult ones to do, just because the glass transition temperature is below room temperature. It's a very steep curve all the way from room temperature all the way till my T sub M. And that's what I want to do. I want to quantify and qualify what that slope is. So I just happen to know because of polypropylene, I went into Moldflow and says, okay, what temperature does Moldflow say I can eject polypropylene at? and it come out at like 230 or 236 degrees, that gives me a starting indication. From there, I can just start saying, okay, start at 230 and I'm going to bump it up to 240 and see what I get. Then I'm bump it up, maybe drop off another second of cooling and get to 245. Start going there. A lot of it has to do with the heat coming out of the core. I want to make sure that I pull as much heat out from the core. And the way I determine this is I put my camera on the part. When it comes out, if my temperature starts to rise, that tells me I have more core heat still coming out. If my temperature stays the same and starts to drop, I know that I pulled out a majority of my core heat. So one of the questions we're kind of toiling with is, do I need to pull out 100% of my core heat, or can I be at 80% skin, 20% core? If my skin comes out cold enough, I can raise the temperature a little bit and then start dropping and not have a problem. So polypropylene, polyethylene, and TPO is a little bit more of a delicate dance, but I'd love to work with you guys and see what we can do to optimize it.
Great. How much does wall stock play into determining ejection temperatures, since the Modulus is a product of both wall stock and material properties?
That's a great question. That's something that I've kind of struggled with a little bit. So your modulus, so your rigidity is equal to modulus times moment of inertia. So a lot of that has to do with, if you have ribs in compression, ribs in tension, you're going to have higher modulus and bending forces, so on and so forth. But from what I've seen, your DMA, my modulus or that TG or the glass transition, wall thickness hasn't necessarily played much of a factor other than thicker walls take longer to cool. But I've also noticed that when I start getting for polycarbonate, if I want to kick out at 300 degrees Fahrenheit, my cycle time is going to be longer for thicker, but 300 degrees Fahrenheit, my modulus should be very close and similar to that 300,000 modulus, 280 or whatever it was. Thicker walls take longer, but I've kind of found that demolding temperature, what we use on those DMAs, those numbers correlate very, very well.
Excellent. Well, here's a kind of an observation, but I wonder if you have any comments on it. Someone says that recovery time is 70% of our restriction on cycle time. We have been doing thermal imaging for part out temperatures and establishing cycle times for about 5 years for huge savings. Is that something you're seeing out there? Does that correlate to what you're talking about?
Recovery is a large portion of it. And that's the big question is, can I get back fast enough? If you do thin wall molding, and I'm working with a lot of customers that do, back in the day, like I said, I've been doing this for 30 some years. And I would say back in the day, 80 thou wall, 80 to 100 was kind of standard nominal wall. Now when I talk about standard nominal wall, I'm at 60 and maybe even 40 thou. So things are getting bigger, better, faster, stronger, thinner, and things are changing. So when you start having very, very thin wall and getting that 12-second cycle time or 10-second cycle time, you're pulling that heat out very, very quickly. My heat comes out faster with thinner walls, but yeah, it's all my plastification time. And that is one of the limiting factors is, can I get back fast enough? So if you're designing a tool and you have a multi-cavity stack tool and you want fast cycle times, make sure that we know and understand how much plastification time I have to get my cycle. Other than that, like I said, you need to have the right shot size, get back fast enough. And also know that the faster I rip back, I'm raising my melt temperature up slightly. Plastification speed or recovery speed has a larger effect on melt temperature than back pressure does.
Good. Someone wants to know about you mentioned you're looking for partners in some cases for the study, and what kind of time investment or work investments required for somebody to partner with you guys on a study like this?
That's a great question. Honestly, it shouldn't depends on how deep you want to get into it. Me personally, I would love to do something with propylene, ethylene, nylon, acetal, polycarbonate, ABS, PC ABS. But a lot of it is just kind of comes in. And what we need to do is determine polycarbonate. I want to come in and add, 2 seconds or keep reducing cycle time and get that slope to say I can pull out 4 degrees a second. And I need to do this on aluminum tools. I need to do it on stainless tools. I need to do it on good design, bad design. And I need to know what the best of the best is. So a lot of it kind of comes down to just coming in, working with us, and saying, hey, this is what we get. Maybe we could try different resins. It shouldn't take a lot of time and effort, but as much in time and effort as you guys would like to provide, the more we can partner, I think we can make all of us smarter.
Yeah, terrific. Yeah, collaboration is always a key to some innovation and doing some of this. In the example that you mentioned, varying ejection temperatures not produce a change in part size. Is this at all counterintuitive to any other data manipulating part size as cooling time is a common factor? And if so, why or why not?
You know, that is one thing that I struggled with. I do believe in my crystalline polymers, and I've done a lot more with amorphous. And this is where I need to learn and partner with somebody on the crystalline polymers. So the crystalline polymers, you build crystals between T sub M and my T sub G. So basically your propylene, ethylene, acetal, you're building crystals at room temperature. You're still building crystals. So typically the rule of thumb that I use is the temperature that my mold is set at is the temperature I build the crystals at. So let's say that I run a 100-degree mold steel. So my crystals are set up, you know, at a minimum of that 100 degrees Fahrenheit. So if I'm at room temperature, I shouldn't be building crystals because I build crystals to that 100 degrees. So the rule of thumb that I like using is find the maximum temperature your part's going to see. That should be your mold temperature, because you don't want to continue crystallizing over time. They say with acetal and a lot of different resins, run hot molds. And the reason they want that is to build your crystallinity and build that up. Now, I'm building crystals between my T sub M and my T sub G. If I'm running a cold mold, yeah, you're going to build crystals at a different rate. So kicking it out hot, my part's going to stay hot longer, and I'll build crystals, more crystalline structure. So I'm going to get more shrinkage, I would think, on a propylene, ethylene, TPO, acetal than I am if I quench it and hold it in the tool a lot longer. However, the big point is time and temperature synonymous. So even though it got there within an hour or 2 hours, over time, or once it sees heat, the Twin Cities here, we're at 90 to 100 degrees last week. You put that in a trunk of a car, you can hit high temperatures and things are going to start tending to twist and warp and continue to build crystallinity. So on my amorphous, I have not noticed dimension changes. In my crystalline resins, you definitely can if you don't run hot molds or if you need to do this. So make sure that we know and understand before building the tool, we get the shrinkage of what we want, what we need, and go from there. But I would say for crystalline tools, it's more of a chance to change. But once we know that, lock it in, it should stay consistent.
Great. Is there a recommended IR camera that you can talk about? Is one better than the other when looking at a thermal camera for something like this?
You know, I have one. I actually bought mine from John Bazzelli. It's, I'm not even sure the name of it. It's not a common name. The big one are Fluke, FLIR, and there's an optics one that I was actually at a show in Detroit. And if you email me, I can give you the name of the guy. It's Optics IR or Optics something. It's actually mounted on the press. It's a portable one. And they said that they can get into it a lot cheaper. I think there's really not much of a difference. The big difference between the cameras are the max temperature it goes up to, because you can get portable ones that actually go on your iPhone, but they only go up to say 250 degrees or 300 degrees. I think mine goes up to 700 degrees. So if you're running high heat polymers, you may need something higher. The number of pixels that it does. And then the thing that I like the most is that floating maximum, where it finds the maximum temperature, my minimum temperature. So when I just put it on a purge, it finds where my maximum temperature. I don't have to cross point and hit that spot. I guess I don't necessarily, I haven't done enough research to say which one's better, but I'd love to learn and see what you guys have.
Great. A few more questions here. Is there a good calculation based on material parameters to determine a cycle time for quoting?
That's exactly what I'm working on. So that's one of the things that I'd love to partner with somebody on, because right now, you know, we're using estimations, but like I said, let's say that I'm running a polycarbonate, I'm running at 515 degrees or 525 degrees. And I know that I can kick it out at 300 degrees. That means I got to pull out 225 degrees. How fast can I pull that out? Now, once again, now that has an effect of mold steel temperature, wall thickness, how quickly I can pull that heat out. And I'd like to know that same thing. Polycarbonate, I pulled out 4 degrees a second. Can I pull out heat? Obviously, thinner walls pull heat out faster. There's less heat come out. But I want to go from my processing temperature till I hit my TG. And then I also want to do from TG till I get all the way back. As I start getting closer to my mold steel temperature, it's going to asymptote out where it's going to start leveling off. But those are the things I'd like to do, is work with somebody to say, hey, this wall section, this thickness, melt temperature to TG, how long did it take? And come up with factors, because that's what I like to do, is come up with a better way of quoting cycle times.
Great. A couple more questions. Somebody out there uses this on 30% glass fill nylon 6. They find that need to be below 360 degrees Fahrenheit to prevent blowout in this section part. Is this just due to having to create a thick enough skin to keep the hot plastic from pushing through?
Well, if they're saying blowout, I'm assuming that means they're using a foaming agent, because typically I don't have blowout. So that's typically what happens is if I'm running glass filled nylon with a foaming agent, and if my internal core temperature stays hot, and once again, if I take my temperature, hold your camera on that temperature. If my temperature comes out at 300, would you say 360 degrees?
Right.
360. And my temperature may come out at 360 at my skin, but then all of a sudden it goes 360, 362, 365, 370, 380, 390. If it starts rising, that tells me my internal core temperature heat hasn't come out yet. And I have had that where a foaming agent, all of a sudden my skin I don't have enough skin and my temperature, and all of a sudden it starts blowing out or having issues. It could also be possibly with gas assist. We've done some things with gas assist where that internal pressure is there and you don't relieve that pressure, those pucks. I don't know how many times I've molded gas assist. They have those overflow pucks. They throw them into the dumpster or the Gaylord, and then probably a couple minutes later, they're popping and scare you. So yes, I would say that has to do with the skin core heat coming out and pressure.
Right. Yeah, this person says they're not using a blowing agent, just very thick sections of the part. So it could be some of the other things you mentioned.
Okay.
Interesting anyway. How much do DMA curves change among specific grades within the same class of materials?
That's a great question. Your polycarbonate typically is polycarbonate. You do get changes with, I actually have one that I was going to include in this. I wanted to get some more information for the seminar, just timing didn't work out, but I have a DMA showing a polypropylene with a nucleated polypropylene, just to say, hey, what kind of modulus difference do I get by having that extra crystalline structure? So there are things that can change, but typically I would say the rule of thumb is very, very close. Your TPOs, when you have a blend of propylene ethylene, depends on the blends. Your PCABS or any of your alloys are going to vary significantly, because if you have PCABS, you can be 90% PC, 10% ABS, or you could be 75-25 or 50-50. But if it's just a straight polymer, rule of thumb is they're very, very close.
Yeah, okay, excellent. Well, with that, we're out of time, and no more questions to answer either. We've gotten through them all. So that's maybe, well, one more. It kind of came in. We have time to get to it. Got a couple minutes here. Do colorant slips and other additives substantially impact a DMA curve? Sounds like an interesting question. Anyone?
More so on your crystalline resins. So because your crystalline resins, we talked about crystallinity, nucleants, they add as a nucleating agent. So your fillers, your colorants, your phthalo blues, your reds, they work as a nucleating agent. So absolutely 100% on crystalline resins. I have not noticed on amorphous resins there's much of a difference, just because I have my glass transition and that's it. I'm not building crystals. I'm not changing crystalline structure. On crystalline resins, I would say 100% yes, it does make a difference. And that's where I have my the DMA curves of a crystalline versus polypropylene unfilled and a nucleated unfilled. And look at that. But yes, they do make a difference specifically for crystalline resins.
Terrific. Well, Sean, that's it for this webinar. I want to thank you for attending this Plastics News webinar presented by Amco Polymers. We appreciate all the great questions that came in, and lots of great ones that Sean answered. And I want to especially thank Sean Mertes of Amco Polymers for hosting this webinar and for answering many of the questions that you had, and for thoroughly putting us through the process that he's gone through with demolding temperatures. It was terrific. If you have further questions or want to reach out to Sean directly, his contact information is on the screen. He'll be glad to get back with you if you're talking about, you have questions for him or want to talk about partnering or anything else. Finally, you'll find today's presentation by going to the webinar section of Plastics News website. This presentation will be posted within 24 hours of today's webinar. Again, I want to thank everybody for attending this webinar, and we'll see you at a future webinar.
Thank you.